All right, so we're going to look to if there is an association between foot length and height. And you might recall we did something like this in Algebra 2, where you guys measured your foot length and measured your height, and we looked at something like this. So the first thing you're going to do is enter the data into your calculator and then create a scatter plot. So, I did provide the notes that has the screenshots of what to do in case you've forgotten, but you're going to remember to go Stat, Edit, and I already entered the data in L1 and L2. But it dawned on me, I thought, I don't know if you guys know or will remember how to clear out something. So I had some stuff in L3. If you want to get rid of what's in your list, you go up to the top of it where it's highlighted in the name, and then you just hit clear and hit enter, and that clears out everything in the list. So go ahead and pause the video, enter all the data into your calculator. And once you have that, then we're going to create a scatter plot. So it's second. Actually, before I do that, let me hit the y equals and see I have some stuff probably from Trig last spring. And if we go second and then stat plot, so I'm going to choose plot 1. The first one is our scatter plot. And wants to know where my data is. There's a shortcut to L1, see in the blue above the L1, so you're going to hit second and then 1, the number 1. And that's already L2. So if I do zoom stat, which is number 9, or you can scroll down, well, that looks interesting. What do I have going on here? I'm guessing if I go to second format, I have my grid on, so let me get rid of that. Okay, so here's my plot. I have my axes turned on. A lot of times, I like to turn those off, but we can see a scatter plot. And I said, if appropriate, calculate the correlation coefficient. So think about what that means. If it's appropriate, well, how do you know if it's appropriate to calculate the correlation coefficient? And remember, that is when I say the correlation coefficient, we are talking about R. The correlation measures a linear association. So it's only appropriate if it appears to be a linear association. So it is appropriate because if I look at this, this data, it looks like a fairly linear pattern. So I would say that it appears to be linear. So then I'm going to go ahead and I'm going to quit this menu and go Stat, Calc, and we're going to choose, I don't want that first one, just get in the habit of not doing that. And we're going to go down to number 8. You can actually just type in number 8. And I have, I don't want a frequency list, so I'm going to clear that out. Yours probably didn't have it. And then calculate. So remember, it has to be L1 and L2 since that's where our data is. Oh, remember when this happens. Okay, so now I have to go, hopefully you remember what to do because it's not a big deal. Second catalog and type in a D because we're going to go down for diagnostic on. This, I probably haven't used this calculator to do this. Okay. But it's good to have come up because it could happen to you. I'm going to hit number 8 and go down to calculate because it wasn't telling me R, and now it will. Okay, so I get this information. So now we know that R is equal to 0.9251. So let's think about what that means because now I asked you to comment on the association. So this is fairly strong. Remember the little number line I showed you? So there, and notice it's positive, and we also saw from the scatter plot, we can see that. So there is a strong, positive, linear association between foot length and height. Okay, I've commented on the association. Remember what that means? Direction, strength, and form, and then if there were any unusual observations, we would comment on those. Okay, so here were the screenshots, just so that you can come back to them if you need to see what I did. I actually named a list. I named a list called foot and one called height. And yes, I know how to spell, but it only lets you do 5 letters. So, but you can do L1 and L2 either way. So we see that. Again, this has the steps for you. So when you look back, if you forget, so you know what to do. And then this had the information, and you can see our value for R. Now, notice that we also see a bunch of other stuff, including, so we'll go here. You see a lot of other things, including this equation right here. And notice the format of it. Y equals A plus BX. So this is my slope. And if we had chosen the other one that did linear regression, it's AX plus B, but this is the one I want you to use. And so this would be my intercept, also a constant when we're looking at that. So we have this equation. Now, you could write the equation like this if you fill in the values. We could say Y equals 41.07 plus 5.18x. So I could use an x and a y, but you don't want to do that, because if you use an x and a y, you have to make sure that you define your variables. So if you think, oh, I might forget to define my variables, then do it this way. Height, and we can spell it right, equals 41.07 plus 5.18 foot. You could say foot length, but this is better to actually just use the words. And that's a good way to describe this equation. This is a linear equation. And this line that's drawn on here on the calculator, that actually is a line, and it's called the line of best fit. And I had planned to show you something with some data here, but I'm going to have to show it to you in class instead, because I can't access that on this computer. So we'll have to do that another time to tell you how it gets its name. So I'll show you that in class later. Anyway, so we have this equation. Now how I got it to draw on here. So if you had gone, if we do this again, I'm going to go back through there because you kind of have to know what you want to do. If I hit this again, and this stands for store regression equation. And I want to store it in Y1, and there's a shortcut key, I believe it's F4, yeah. So you can actually store it, and if I calculate, I don't see it at that point, but now hit graph, and it graphs that line for you. So this is actually it's our line of best fit. It's also a prediction equation. And if we wanted to predict the height of a person based on their foot length, this would be the best line to do that with. Now, we have a symbol in statistics to show that something is a prediction equation, and it's a statistic, and that is this little hat. And that's how you would say that, hat. Height hat, or Y hat, equals 41.07 plus 5.18x. I prefer words, but you use that little hat symbol to show that we know this is a statistic. If I were to know somebody's foot length and used it to predict their height, it's a prediction. I have to make sure that I'm clear in my communication, that I understand that that doesn't mean that person is going to be exactly whatever height we come up with, but it's just it's predicting that. So this is the process called linear regression, and we're going to be using that. It's really important, and actually let me rewrite this. So we had height, (5.18x). Oops, foot. It's really important that you know how to interpret the slope on a regression equation. So if you think about how you interpret the slope for just a regular linear equation. As you increase the x value by 1, the y value increases by whatever the slope is. Okay, that's what that slope of a line is, or it could decrease. So an interpretation of slope in the context of this problem, as the foot length increases by 1, and we're going to have to make sure we know what our data was. We had centimeters for both. So as the foot length increases by 1 centimeter, the model predicts the height will increase by about whatever the slope is, 5.18 centimeters. Okay, so you want this on your interpretation of your slope. You have to make sure you are able to interpret the slope in context. Some of the things that you really want to make sure that you include is this idea, the model predicts. Communicating, don't say as the foot length increases by 1 centimeter, the height will increase by 5.18 centimeters. That sounds like it's a sure thing, and it's not. This is what the model predicts. Might be right, might not be. And you can also kind of put in the word about 5.18 centimeters. So those are important things to include when you are interpreting the slope or the rate of change of this problem. So interpretation of the y-intercept. Okay, so that's this. So think about what a y-intercept is in just basic math. You let x equal 0 and you solve for y. So this would be saying if the length of the foot was 0 centimeters, which obviously makes no sense, the model predicts the height to be about 41.07 centimeters. And then I'm going to say this makes no sense. You can't have, I mean, a person with, if that has no foot length. So it kind of breaks down. And that's actually, that has a name too. It's called extrapolation. Clearly, this goes outside of our data. If you look back at our data, we were dealing with foot lengths between 23 centimeters, 28.5 centimeters. So this 0 centimeters doesn't really fit into our data set at all. That's called extrapolation and not a good thing. But anyway, this is how you interpret the y-intercept. So you always want to make sure that you interpret both the slope and the y-intercept in the context of the problem. So we've already talked about R, that represents the correlation coefficient, and it measures the strength of a linear relationship. So we've talked about that already in Chapter 7. But your calculator also, actually let me go back to one of these screens. The calculator also reported the value of R squared, and it's right here. And what that is called the coefficient of determination. And that has an interpretation as well. And how do you get R squared? You square the R. Yep, it's that easy. So that actually is, if you took this value of R and you squared it, you would get this value right here. So it's approximately, it's 0.86 if I rounded to 2 decimal places. So I'm going to state here that R is approximately 0.86. Okay. So what does that mean? How do you interpret that? Because this has a very distinct way it needs to be interpreted as well. So this is what it says. 86% of the variation in height can be explained by the changes in foot length. Okay, now I'm going to underline some parts here. This right here is r squared. Oh, I should have put r squared right here. Oops. So this is the r squared value. This is like a fill in the blank. 86% of the variation in this right here, response variable. Can be explained by the changes in explanatory variable. And that is how you interpret the coefficient of determination in context. So these little places where I drop the green lines, you're going to drop the context into that problem. So r squared percent of the variation in response variable can be explained by the changes in explanatory variable, and you put the context in. And then you will always have that interpreted correctly. Same thing with slope and y-intercept. If you think of this kind of as just a model of how you always interpret the slope of a regression equation and how you always interpret the y-intercept of a regression equation, you'll be good. All right, so now this last thing that I want to show you, let me set it up here. If I go back to my regression line, okay, that we drew here, and notice that the data is not all on the line, okay? So this one misses by a little bit. This one misses a little more. It's above the line here. Mr. Brinkman would like that. This one's below the line, below the line, below the line. This one's above the line. Okay, so some of the points are above the line. Some of the points are below the line. And that difference right here, the difference between what we actually see and what our prediction is called a residual. So a residual is the difference. So we actually find that by taking the observed value minus the predicted value. And that tells us the residual. So sometimes the residual is positive because if my observed value is above the line, then the predicted value is on the line. So observed minus predicted is going to be a positive, so that would be a positive residual. If the data point is below the line, then when I do the observed minus the predicted, it's going to be a negative value, so that would be a negative residual. So these are all called residuals. So this last screen that I have shows something called a residual plot. And I'm going to show you how to create that on your calculator. So what we're going to do in our, let me just mention this. When you do linear regression on your calculator automatically creates a list, and you can find it by going second and then hitting the stat key. And look at the very bottom one down here, it says resid. Those are the residuals for my regression I just did. And your calculator automatically, when you run this regression, it automatically stores it in a list called resid. So every time you run regression, linear regression, it's going to replace your residuals with whatever you just did. So it's just like a temporary storage. But we're going to go ahead and create this plot, a residual plot, and then I'll show you what we use it for. So I'm going to go to my plots and go back to plot 1. And I'm going to leave my x values the same. And my y values, I'm going to plot the residuals. So I'm going to go second, list, resid, and choose that. Okay? Now, I need to go into my y equals. First of all, I don't want it to graph this line. So I'm going to just turn it off. So you just go highlight the equal sign, hit enter, it just toggles it. And what I want to graph instead is I'm going to graph the line y equals 0. Because really what the residual plot is doing is it takes this residual line or this regression line, and it's like making it horizontal, straightening it out. Well, I guess it's straight, but it's making it horizontal, and then you're seeing the residuals above and below the line. So it's just changing the way that you are looking at that graph. So we're going to plot this. So this 0 line actually represents the residual line. I'm sorry, the regression line. So now I need to have it redo the zoom feature for me. So I'm going to do zoom 9 again. Zoom stat. Yep, it's 9. And here you see that graph. So you can see that I get that same thing. So then what this means is this is showing the residuals. Again, it's showing the ones that are above. So like here's a residual that's a positive residual. You would find the value by taking the observed value minus whatever the predicted value was. Then we have some that are negative. This has something to do, if you added up all the residuals, by the way, you would get 0 for the least squares regression line. That's part of how it comes about to get that particular line, which is what I was going to show you, and I will in class. But this is, again, the residual plot. Now, you're looking for something in a residual plot. So residual plot can help us. So this can help us determine if a linear model is appropriate. Okay, that is not how we spell that though. Okay, that's better. Now, remember, we also looked at, before we could determine if we wanted to use R, we looked at the data. So, you can kind of look at the data and see if it appears linear. So that was one thing, is the data appear to be straight enough? But sometimes there can be a very slight curve in the data, and a residual plot can help us see that. So what we're looking for in a residual plot is a random scatter above and below the line, this 0 line, which represents my regression line. So we kind of have that. What you don't want to see, so sometimes you can see something like this, where the points are really close to the line at first, and then they fan out, and like they get bigger, like, so they're kind of fanning out. That would indicate not a linear model. Sometimes you get data that looks like this. And you might look at that and go, oh, it's a line, it's linear. You don't want a line in the residual plot. You don't want a pattern. This has a pattern. So this would tell me that my data was not linear. Okay, so what you're looking for in a residual plot is a random scatter above and below the lines. You don't want to look for if you find a pattern, then that tells you that it's possible, it's some other type of model. It could be an exponential model, could be a power model, some other type of function, but not linear. So that's what you're looking for in a residual plot. So that was kind of like a really quick trip through linear regression on your calculator. But now you'll have some notes, and now you'll have this video. If you ever need to look back, if you forget the steps, you'll know what to do.